Hello, students. Welcome to today's Explainer. I'm your professor, and today, in this masterclass, we're going to decode a super important chapter from your computer science syllabus. Chapter 7, Relational Database and SQL. This chapter is incredibly high-scoring for your exams, so go ahead, grab your pens and notebooks. Let's get right into it. Here's the agenda for today's session. We'll start off with database concepts and architecture, move on to data abstraction, relational terms, SQL data types, and finally, we'll wrap up with DDL, DML commands, and functions. We're covering it all, from basic to advanced, so we're absolutely not leaving anything out. So let's dive straight into Part 1, Database Concepts and Architecture. First things first, what exactly is a database? Well, think of a database as an organized collection of logically related data. It's stored in a way that lets users retrieve it super quickly. Think about everyday examples, right? Like a hospital, a school, or a bank database. It's really all about keeping that massive amount of information perfectly organized and instantly accessible. Now, this data hierarchy is a massive exam or revision highlight, so you'll definitely want to remember this. It all starts with raw data. That data comes together to form a field. Then those fields combine to create a record. A collection of records gives you a table, and combining those tables, well, that builds our complete database. For example, in a school database, student would be a table, and all the details for just one specific student, like Akash, makes up a single record. But how do we actually manage all this data? That's where we need specific software, which we call a DBMS, or Database Management System. Essentially, it's a set of programs that gives you, the user, the power to define, create, and maintain a database, all while keeping access tightly controlled. You've probably heard of some of the big ones, like Oracle, MS Access, or SQL. This entire architecture relies on four main components: the users, the database application, the DBMS software itself, and the actual database. So why do we use this system? The advantages are pretty clear. It massively reduces data redundancy, duplication, and keeps your data consistent across the board. The downsides? Well, the setup costs can be kind of high, there's always a risk of system failure, and you've got to keep up with regular upgrades. Moving right along, let's jump into Part 2 and see how data abstraction and database models actually work. Data abstraction is actually a totally fascinating concept. Simply put, it's about only showing the user the details they actually need while completely hiding all the irrelevant background stuff. There are three levels to this. Level 1 is the physical level. That's the lowest one, which deals with how data is literally stored on your hard disk. Next is Level 2, the logical level, which defines the data structures and relationships. And finally, Level 3 is the view level, the highest tier, where end users like you and I actually interact with the database. There are a few different models for representing data. This pops up in exams all the time, so pay close attention. First up is the hierarchical model, where records are organized kind of like a tree structure. Then there's the network model, which relies on links and graphs. But our main focus today is the third one, the relational data model. Here, data is structured in tables with rows and columns. It's super easy to understand, though if the database gets too massive, it can definitely put a heavy load on your hardware. All right, let's hit Part 3, Relational Database Terms and Keys. Okay, students, you really need to memorize these terms. This is the essential vocabulary for relational databases. A relation simply means a table. Attributes are just the table's columns. A tuple refers to each individual row or record. Cardinality is your total number of records, while degree is the total number of columns. And finally, a domain is the set of all possible logical values that can go into a specific attribute. Make sure you lock these into your brain. To uniquely identify these records, we use what we call database keys. There are four essential types you've got to remember. The primary key is the attribute that uniquely identifies every single row. It's always unique and absolutely cannot be null. Candidate keys are all the keys that actually have the potential to be the primary key. Whichever candidate key doesn't get picked for the top job, that becomes your alternate key. And finally, a foreign key is one where its value comes directly from the primary key of a totally different table. All right, now we're getting into the really practical coding side of our explainer. Part 4, Introduction to SQL and Data Types. SQL stands for Structured Query Language. It was actually created back in the 1970s at IBM, and it's what we use to access and manipulate databases. It's so intuitive and portable that you don't even need complex procedural coding. SQL statements are basically broken down into four main categories. We use DDL to define data structures, DML to manipulate the actual data, DCL for data control, and TCL to handle transactions. Here's another major exam tip for you. Know your SQL data types. Integer is used for whole numbers, while decimal is, well, for decimals. Char stores fixed length strings, whereas varchar is for variable length data. The biggest advantage of varchar is that it actually releases unused memory space, a real game changer. Beyond those, you've also got date, time, Boolean, and the memo data type for handling massive blocks of text. Moving right along to part 5. Now we're going to dive into the exact syntax for DDL, constraints, and DML commands. It is absolutely crucial that you understand the difference between these commands. On the DDL side, which deals with the overall structure, we have create to make a new table, drop to delete one, show to display it, and alter to modify it. But when we want to play around with the actual data inside, that's when we switch to DML. We use insert to add a new record, update to modify existing data, delete to remove rows, and select when we want to view specific data. When we're creating a table, we often apply constraints. Think of these as mandatory conditions the data literally has to follow. For instance, not null ensures a field can never be left empty. Unique guarantees there are 0 duplicates. Check is used to validate a specific condition, and default just drops in a standard value if the user forgets to enter one. Finally, let's explore part 6, SQL operators and aggregate functions. To filter our data, we use operators, usually tucked right inside a where clause. We have your standard arithmetic operators like plus and minus. For comparisons, we use relational operators. Then there are logical operators like and or. But we also have some incredibly powerful special operators. Between checks a specific range. Is null hunts down missing data. Like is used for pattern matching, and group by collects data across multiple records. When we need to perform mathematical calculations across multiple records, we rely on these 5 aggregate functions. Count gives you the total number of non-null records. Min finds the absolute lowest value while max grabs the highest. Sum adds everything up for a total, and AVG calculates the average. Easy, right? Let's see how these queries actually look in practice. For example, if we wanted to pull the data for all male teachers from the teacher table, we'd write select name, salary, age from teacher where gender equals M. And what if we need to update Sham's salary? We'd write update teacher set salary equals 28,000 where name equals Sham. It really is that straightforward once you get the hang of it. So, students, our explainer has officially covered Chapter 7 in full detail. Now it's time to test yourself. Drop your answers to the 3 quick revision practice questions into the comments below. But before you go, think about this. In today's world, every digital footprint you leave, every like, every swipe, is being stored in databases just like these. If you had the chance to build a global database, what exactly would you want to track? Keep studying, keep coding, and I'll see you in the next one.